In this video, I would like to show you an application of Rolle's theorem. So recall, Rolle's theorem tells us if we have some function defined on an interval a to b, and the function at a is the same thing as the function at b, maybe it goes up, maybe it comes back down, but at a and b it's the same value, the function is nice, it's continuous and differentiable, then somewhere the derivative must be 0. Somewhere the slope of your tangent line is horizontal. So that's what Rolle's theorem tells us. Let's look at an application of this. I want to show there is exactly one solution to the equation x cubed plus x is equal to 2. Exactly one solution. So you might look at this problem and say, that's not hard. Let me just try and plug in some values. 0 doesn't work, 0 plus 0 is 0. But try x equals 1. Sure enough, 1 cubed plus 1 is 2. There's a solution, right? Here's my solution. X equals 1 is a solution. And you're right, x equals 1 is a solution. Very good. But I want to show there's exactly one solution. That is that there's not a second solution. We found one. How do we know there's no other solution? You might try and plug in 2. That's not going to work. It's too big. Maybe try, -1. Well, no, that's not going to work. You can try to reason through this, but how do we know there's exactly one solution? There can't be a second solution. Well, Rolle's theorem can help us here. Suppose there were two solutions. Suppose we had that your f of a and f of b, two different values, a and b, both came out to equal 2. Okay, so what is my function f here? Well, I guess I should define this. So let me just define my function to be my function right here. F of x will be my x cubed plus x. Okay, then suppose there were two solutions. So sum a not equal to p, two different solutions. We already know one of those can be 1, but we're saying suppose there's a second solution. Then by Rolle's theorem, you would know that the derivative of your function has to be 0, somewhere between a and b. There's some value where my derivative comes out to be 0. But what is my derivative? If this is my function f of x, then my derivative will be just 3x squared plus 1. So that means that the derivative at some place c would be just 3c squared plus 1, and that has to be 0 somewhere, right? Since this guy is 0, he must be 0 somewhere. That means, solving for c, 3c squared is -1. But you see the problem now? How can 3c squared be -1? For that would mean that c squared is -1/3. But you can't square a number and get negative, at least not a real number. So there's no solution exist. This has no solution. No solution. What went wrong? Well, either we can't use Rolle's theorem here, but we can use Rolle's theorem because this is a nice function. This is a function that's continuous and differentiable. So both those conditions are met. So Rolle's theorem is fine. So what must be wrong is this first condition, that f of a equals f of b. This assumption that there are two different values must be false. So just to review, we said if there were two solutions, then we have somewhere f of a equals f of b, they're both equal to 2. But then you have the derivative has to be 0, but there's no solution to the derivative being 0. So the assumption that f of a equals f of b is false, so we can't have two different solutions to this guy. Okay, it's kind of a strange way of reasoning, but hopefully this shows you some of the power of Rolle's theorem. Indeed, you can also just graph out this function. If you graph out this function, x cubed plus x, what do you get? I think it looks something kind of like this. It's going to look a little bit like x cubed, but then skewed by adding the x to it. And you're going to see, well, that's a function that's always increasing, since its derivative is always positive. Since it's always increasing, that means that you can't have, of course, the derivative is never going to be 0. It's always positive. So that's another way you can think about it, but hopefully this helps you to see an application of Rolle's theorem.